And if you feel like that conversation too harsh for you, please just let me know. But just the reality is the honest truth right now. All right, today we are going to finish up the notes. Again, I encourage you to have actual notebooking stuff with you. Okay. Bailey, I don't know the answer to that, Bailey. Not really. You need to be here. Like, that's why you're here. Maybe have a conversation with people at your house. Find a quiet spot. I mean, I don't know what to tell you. All right. So today we're gonna finish up the notes and then go from there. All right. So we were for the last few days we've been talking about the Big Bang Theory and the evidence behind the Big Bang Theory and the start of the universe. I've been grading some of your work on there. We still have a few misconceptions that we want to address. Again, especially with the discussion one, a lot of kids were talking about the Earth and rewinding the history of the Earth. While that's yes, that's part of rewinding the tape, the movie of light of the universe. That's a very, very small portion. I don't know if you guys have ever seen the like timelines of how long humans have been on Earth and all that kind of stuff. Like if you took the entire history of Earth and you made it into a 24-hour day, humans have been on Earth for 1 second. Um, but the history of Earth compared to the universe, Earth has been there in a fraction of time too. Okay, so there's a lot of things that happened before Earth even came around. Okay, and so again, the Big Bang, the universe, we're not just talking about our planet. So again, there was a big misconception still happening with that, and I want to make sure that we're okay on that. So we're going to start again, kind of talking a little bit about what Hubble realized. So we talked about the universe expanding. We did a lot with that Monday with the red shifting and the fact that light changes colors. Not just light, but all electromagnetic radiation. It shifts depending on if the object is moving. So if it is moving away from us, it shifts towards a larger wavelength in a redder color. If the object is coming closer to us, it shifts to a smaller wavelength because the wavelengths are being compressed together. Or in light, we say that blue shifting. And so Edwin Hubble in 1920s, he's actually one of the first scientists to realize that there's more beyond our galaxy. I think we talked about that already. And essentially, telescopes were able to get good enough to see beyond our galaxy and to see that those little white twinkling dots in outer space are not actual stars, but entire galaxies. So, for example, this picture here, this is a real picture. If you can actually, with the right telescope, you can actually see this. All of these dots in this picture are not stars. They are galaxies, entire galaxy. And many of them are bigger than our own galaxy. And you notice that they are colors. They have different colors. They have different wavelengths, different frequencies that they're presenting themselves. And this is kind of the data that scientists can collect. Okay, is the fact that can we measure where these galaxies are? And then if we can't measure it, can we collect the radiation data to show that it's moving further or closer away by red shifting or blue shifting? So again, most of what you see when you look up into into the sky, while a lot of it is stars, for every star that you see, there's an even more galaxies out there, and so there are a lot of galaxies out there beyond our own Milky Way that we have. Okay, and to be honest, the Milky Way galaxy isn't really all that special compared to all the other galaxies that we have. So this is a picture in the top corner, a picture of the Hubble telescope. He did not make that telescope. It's named in his honor. But that telescope, I think it's been launched since 1960s, 60s or 70s, I think. But it's constantly being updated with new technology. So one of the reasons why a lot of astronauts go into outer space, especially in the 90s and early 2000s, was to actually go up and modify the equipment that's already up there. And so we would actually launch telescopes and other things, satellites, and the astronauts would actually go up there and fix them and update them. And so the Hubble telescope is something that we continuously update and kind of fix with those astronauts. So they do a lot of training to go up there and figure out how to fix the Hubble telescope or how to make it better. And we are making it better. There's actually a really cool idea right now called a virtual telescope or a digital telescope, where they're taking images from all around the world and combining them together. And that's how we saw the black hole a couple years ago. I don't know if you remember that. That was pretty cool. But anyways, all right, so Hubble's law is something we haven't really talked about. But again, Hubble observed that most of the galaxies moving away from each other, they're redshifting, and he was able to calculate how fast the universe is moving, or how fast it's accelerating. And he figured out that the universe is accelerating at approximately 70 or 46 miles per second per megaparsec. Megaparsec is a, for lack of a better word, it is a area, how much, it's a space term for distance and how far light travels. But anyway, it's a really, really fast number. Okay, remember I was talking about tennis ball? If I threw a tennis ball at you that I could change the color, I would have to throw it near the speed of light in order for that to happen. Well, the universe is expanding incredibly fast. So fast that light can change colors depending on what's happening to it. Okay? And so using this rate of acceleration, and again, this is something we can calculate. This is measurable data. Using that rate of acceleration, able to determine that the universe is approximately 13.77 billion years old with a B. Okay? Now, this number is continuously being updated based on data that we're finding. I mean, scientists can actually try to get down to the day based on the rate of acceleration. They're constantly figuring out, how long has it been accelerating. Okay. And again, as we discover new information, new data, we'll change these numbers, okay? And who knows, maybe tomorrow we discover something incredibly unique and we have to rethink this whole thing, okay? It hasn't happened yet. It hasn't happened in the last 120 years, but who knows, right? Again, misconception about the universe expanding, that we're measuring the stars in the sky. The stars are part of our galaxy. Our galaxy isn't really, it is expanding, but that's not really what we're measuring. We're really measuring other galaxies and we're comparing them to each other. Okay, so the galaxies are moving away from each other. All right, we also had two scientists that were observed cosmic background radiation, and this is what the telescope they use, or it's a radio telescope, called a Horn telescope, Horn antenna. So in 1960s, two scientists, Penzias and Wilson from Bell's lab, I think it's New Jersey, I think, they created a Horn antenna, which is this guy right here, and they wanted to pick up electromagnetic radiation from space, and particularly they wanted to look for radio waves. And again, that's a form of energy from outer space. And it was really kind of a funny story. They made this huge thing to listen for sounds in outer space, radio waves. And every time they got in there to record data, they picked up noise. Every single time, every single second, they picked up noise. And it was kind of a non-stop static. And they were very discouraged, thinking that they were doing something wrong, or thinking that they were hearing stuff from birds or cities and things like that. They actually had to go in there every single day and clean it, because they thought that like bird poop and things like that were messing up their data. So they would go in there and hand scrub this thing every single time they wanted to collect data, just to make sure that there was nothing wrong with it. And sure enough, every single time they listened for energy in outer space, they were picking up noise. But that noise was actually data that they were looking for. Okay. And so they were wondering, where is this noise coming from? Why is it in every direction? Why is it everywhere in outer space? Every time we use this thing, we pick up noise, we pick up data. And it turns out that is the leftover from the Big Bang, or, that's what they theorized, that this is the energy, this is the sound, or the electromagnetic radiation that is left over from the Big Bang noise, or from the Big Bang. And again, it, for lack of a better word, it exploded, it expanded that energy in every direction around the universe. Okay, so they heard this noise everywhere they looked. You can actually hear this really easy. If you have a car radio, instead of turning your radio to Q102, turn it to 101.7. I don't know, 101.8. Turn it to a radio station that doesn't work, and you'll hear static. But that static is energy, and that is the energy left over from the Big Bang. Okay, and it is you collect that energy everywhere you go if you have an antenna, and again, some of it might be localized, but it is everywhere in our universe, even where things are not there, even where there is no galaxy, where there is no star, we're still picking up energy from those places. And so after about 9-10 years, they're able to actually collect that data from all the, because again, you can't look at the entire universe in one day, but they can actually collect data, and they can put all the data together, and this is essentially a picture of what the universe looks like using energy. And all these little red dots are where there are galaxies today, but all these colors, they are the temperature, they are the energy of the universe. Okay? And now these dark blue spots doesn't mean there's no energy. These dark blue spots are almost the exact same temperature as the red dots. Okay, they're off by, I think, the paragraph over here. They're less than 0.0002 degrees between the blue and the red. The red is just enhanced a little bit more just to see where those galaxies are, but this blue stuff is pretty much the same temperature as this red stuff, but there's no galaxy there. So again, why is there temperature? Why is there energy? Why is there radiation where there's no galaxies? Where is that energy coming from? Why is it there? Okay. And scientists believe that it is leftover energy from the Big Bang. Because remember, you can't create or destroy energy. So when the Big Bang had that energy, there it is, and it's going to be there essentially forever. Because you can't create it, you can't destroy it. All right. So there are other less concrete forms of evidence of the Big Bang theory. So again, we talked about the big three, and to be honest with you, just the fact that the universe is expanding is probably enough to support the idea of the Big Bang. Because if you undid the expansion, all the stuff will come back together. We talked about the fact that there's energy everywhere. Again, that's probably enough evidence all by itself to suggest that energy had come from one spot and expanded. And then we talked about the composition of the universe, the elements that are made. Again, that is enough data just by itself to really support the Big Bang. But there are other forms of evidence, and I don't really want to talk about them because I don't really know them very well. But there are gravitational waves as a result of the Big Bang. So you got to remember, there was no gravity before the Big Bang. There was no stuff. There was no mass. There was no universe. And so when it was created or formed, that starts gravity. And so we can actually measure gravitational waves as a result of Big Bang. I don't know exactly how they do that, but that is another piece of evidence. There's also some evidence out there for dark matter and dark energy. This is still pretty theoretical. There's some gaps in our information, and dark matter, dark energy, stuff that we can't see, kind of explains some of that. But maybe we'll invent a new telescope to see that stuff. And again, that's your job. Neutrino formation and concentration. So right after the expansion started, there were formation of neutrinos and other particles that make up matter. And so they can actually measure that. And then the last one is a quasar existence. Quasars are, I don't want to say they're stars, but they're kind of like stars. They're energy bundles, so to speak, but quasars don't exist around us, but they exist really far away. So we can literally look back in time, where there used to be a bunch of quasars, but now there's not. And so the universe is changing over time based on that data that we have there. All right, so there is other forms of evidence. The big three are not the only thing. All right, there are additional resources. Again, if there's anything confusing, I have some kids saying stuff like, I don't get this at all. Watch these videos, okay? I know I'm not the best person to explain the Big Bang Theory. I don't spend all my time thinking about this. So watch videos from Neil deGrasse Tyson. Watch videos from, these scientists who that's literally their job is to be an astrophysicist and understand the Big Bang Theory. Watch those videos, read papers, Scientific America, NASA, all of these guys out there. They put out tons of stuff. Learn from them just as much as you learn from me. Okay. I'm just going to quiz you based on whatever's on the PowerPoint, whatever's in our activities, but you can learn from all kinds of people. All right, today you have a review activity. I'm going to ask you to make 5 flashcards, and preferably a 3x5 inch flashcard. Okay. And you can actually bring them in class and use them on your notes on Friday. We have a quiz on Friday. Or use them on your quiz on Friday, yeah. So today I'm going to ask you to make 5 flashcards. So open up the activity. It tells you what 5 flashcards I recommend you to make. Then take a picture, front and back, of your flashcards, and then bring them in with you on Friday. Okay. All right. So we have about 15 minutes. Actually, no, we got longer than that. We got about almost 20 minutes for you to do your flashcards and then any other work that you're missing after your flashcards. Okay. That's it for me. If you guys have questions, please ask. Please put them in the chat box. Whatever you need to do. Okay. That's your work for today. Again, I hope you finish it today, right now. Get it done. Don't fall behind. Okay, you got 20 minutes. All right, let's do it.